One World Combinatorics on Words seminar. Today, Jeff Shallit is going to be giving us a Walnut tutorial, and we are scheduled to go a little bit longer than usual. So yeah, be prepared that we could go as till well, half an hour longer than usual. So go ahead, Jeff, whenever you're ready.
Okay. So it says I'm screen sharing, but it doesn't give me the opportunity to pick where I'm sharing. So let me try again. Okay. Can you see the slides?
Yeah.
Okay, great. So I'm going to talk about Walnut, which is a tool written by Hamoun Mousavi for doing combinatorics on words. And like Narad said, this is going to be a tutorial. So it presumes you already know many of the things that I'm talking about and just how you would use Walnut to prove or disprove things about sequences like the 2A Morse sequence. The slides are available on my homepage and also on the seminar homepage, or will be very shortly. You can just cut and paste the kinds of things that I'm talking about into Walnut and verify the results yourself. So the slides are intended to be a resource for people who want to use it. Like you can go and look at examples that I'll present and see how to do it. So some of the slides are a little bit busy then because they have all the details there. You don't need to read every detail on the slide. And please feel free to interrupt at any time. Otherwise, I'm likely to just issue a flood of words that doesn't stop for 90 minutes. Also, if you feel like you want to leave earlier, please feel free to do that. Okay, so what's Walnut? Free software program written in Java that can automatically prove or disprove conjectures about automatic sequences. Now, not all conjectures, but many. It will give simple, explicit characterizations of the factors of automatic sequences that have certain properties. It can provide explicit formulas for counting aspects of automatic sequences. It can oops. Still getting used to this mouse. In conjunction with other software, you can use it to heuristically search for infinite sequences having certain properties. And then once you tumble on a guess, then you can prove that this candidate that you found really does have the property that you want. So we'll see some examples of this. If you want to find a sequence that has no squares of length greater than or equal to 4 or something like this, you can just program up a breadth first search and it will give you some candidates, and then Walnut will just prove that the candidate really works. The restrictions are that it's not a general purpose tool. You can't prove all theorems of combinatorics on words with it. You can only use it with automatic sequences. And when I say automatic sequences, I mean interpreted rather broadly, as we will see, not just K automatic sequences. And the statements that it works with must be phrased in first order logic, particular first order logical theory that's an extension of Pressburger arithmetic. And I won't define it formally. In general, I'm not going to do any kind of formal definitions in this talk because it's just an example of how you use things. So in particular, if you want to quantify over sets, I can't do that with Walnut. So Walnut can reprove dozens of existing results published in the literature. Often the proofs that Walnut gives are basically trivial in comparison to pages and pages of case analysis in the literature. It can prove new results. There's about 35 papers published on it by me and co-authors and other people using it. It can correct or strengthen already published results. We found some mistakes in the literature. We found stronger versions of theorems published in the literature and so forth. And if you go to this web page here, then you will be able to look at these papers and you can download Walnut there. And there's a new version of Walnut, which is called, it's still called Walnut, but I call it Ostrowski because it can deal with Ostrowski automatic sequences. And that was written by Asim Baranwal. So that's actually the version I will be using today, is this new version, which you can download here, which was written by Asim Baranwal. Okay, so let's look at, I'm going to present 10 examples basically on how to use it. And let's start with a very simple example. Probably one of the most famous theorems in combinatorics on words is this result about the 2A Morse sequence, which says that it's overlap free. So the 2A Morse sequence, one way to define it is with this fixed point of this morphism. And what's an overlap? An overlap is a word of the form AXAXA, where A is a single letter and X is a possibly empty word. So an example is the French word entente. So here, A is the letter E, and X is the letters NT. So we see ENT, ENT, and then E. So that's an overlap. Okay, so overlap free means it has no factor or block sitting inside it, no contiguous block. That is an overlap. Okay, so let's see, how would we do this? Basically, what we need to do is write down a first order formula that says the 2A Morse sequence has some overlap. And then we just want to show that this first order formula is always false. So if it has an overlap, it must begin at some position I. So here's the ith position Ti. And AX must be of length n. So here the next A occurs at position I plus n. And the third A occurs at position I plus 2n. So this says that this symbol's AXA is the same as this symbol. And if you look at this picture, then what this means is there's some n, which is at least 1, because that's the length of AX. And remember, A is a single symbol and X is possibly empty, such that the block of symbols from positions I to I plus n is the same as the block of symbols from I plus n to I plus 2n. So that's the existence of an overlap is logically equivalent to this statement. And if we sort of break that down a little bit more into individual symbols, it means there exist I and n with n greater than or equal to 1. And for all s from 0 to n, the symbol at position I plus s is the same as the symbol at position I plus s plus n. So there we have a first order logical statement asserting the existence of an overlap. Are there any questions about this statement or how I got it? Feel free to unmute yourself and ask if anything is unclear, or type it in the chat. I will look. Okay. All right. Well, so in Walnut, now we just translate this into Walnut. Basically, we take this statement and we translate it into the syntax that Walnut expects. Now, of course, the way Walnut works is you just typing into a text window. And so you're restricted to the ASCII characters. So there is no ASCII character for there exists. There is no ASCII character for all or implies or and. So we just use some substitutes. So there exists becomes a capital E. An and becomes this ampersand. A for all becomes a capital A. And implication becomes equals followed by greater than. And T in Walnut is built in as the capital T. That's a built-in. It has some famous sequences built in, and one of them is the 2A Morse sequence because it's so famous. So if you look at this, I hope it doesn't look too much like gobbledygook. You can read it as there exists I and n such that n is greater than or equal to 1. And for all s less than or equal to n implies this statement. And you might say, well, why isn't there the 0 less than or equal to? That's because the domain of all variables in Walnut is assumed to be the natural numbers. Okay, so we just type that in and Walnut returns false. So this is the assertion that there is an overlap. It has an overlap. This is just a name. This is the instruction to evaluate the statement that follows and give it this name, and it returns false. So I'm now going to do this. So here I am in a text window. I hope everybody can see this text window. and I go to the particular directory. I go to bin. I start up the prover by saying Java main prover. This just runs Java on the code. And there's a prompt. And now what I can do is, assuming that I'm competent to use this mouse, is I can just copy this text and paste it in and hit return. And there, this is the output. This sort of looks like gobbledygook, but basically what it's doing is it's parsing the formula and giving you progress along the way, how much time it takes, how many states of automata it's building. And at the very end, it says false. Remember, the assertion was that it has an overlap. So the fact that this assertion that it has an overlap is false means it doesn't have an overlap. So there, that's the proof.
Jeff?
Yeah.
I have tried it in real time now, according with you, and I don't have the false at the end.
Yes, that's because you're using the original version of Walnut, whereas I'm using the new version.
Okay, thank you.
That it was made by Asim Baranwal and is downloadable. So, but let me respond to that. So, if you're using the older version, then you have to do a little bit more work. Here, it just gives you false, which I think is better. But in the older version, you go to the directory called result. And remember, we named this has OLAP, and you look at has olap.txt. And there it is. Okay, so you should be able to do that in real time then, Stefan, and let me know if you have any difficulties.
I'm in Eclipse. I don't know whether maybe it's a bit different now.
Well, you have to go to that directory because that's where, or use a file search to search for the file has olap.txt and then look at it and it should say false. Okay. So I'm not going to do too many things where I just type stuff in like that, but I will from time to time. Okay. So let's see, now I'll go back and hopefully this will work. Okay, so hopefully now you see all the slides again. So Walnut can determine the truth of well-formed first-order formulas about automatic sequences. What do I mean by automatic?
It is there, thanks.
Great. A is automatic if there's a regular enumeration system, and I'll say what I mean by that in a second, and deterministic finite automaton with output, such that on input, the representation of n, the automaton reaches a state with output an. And examples of these kinds of sequences are 2A Morse, Rudin-Shapiro, Fibonacci, Tribonacci, and so forth. So enumeration system is going to be a way of representing natural numbers by strings. And I call enumeration system regular. Maybe that's a bad name because regular has so many meanings, but every natural number has exactly one representation, modulo the fact that you can have leading zeros. The set of valid representations is a regular language. And the third one is that the set of representations of triples, x, y, z, such that addition is recognizable, x plus y equals z, this relation is recognized by a deterministic finite automaton. So those are the kinds of systems that Walnut can work with if these three conditions are satisfied. And they are satisfied for base K representation, for Fibonacci representation, for Tribonacci representation, for Ostrowski enumeration systems, and so forth. So it's a pretty large class of things that you can represent integers as that it works for. Okay, so I just say that shorter representations are padded with leading zeros so that when we talk about the representation of triples, we read the digits of the representation, the symbols of the representation, bit by bit in parallel, and leading zeros pad the shorter ones. Okay, so some examples of regular enumeration system, as I said, base K, that's built in. and Fibonacci representation, which is built in, Fibonacci representation, and a Straussky representation for quadratic irrationals is built in to this version written by Baron-Wall. And that new version by Baron-Wall also has some minor cosmetic improvements over the old version. Okay, so in the case of base K representation, we know that K automatic sequences coincide with images under a coding of the fixed point of K uniform morphisms. So we can just write down that K uniform morphism instead of the automaton. It's a little bit more compact, maybe. Okay, so now there's a whole theory behind this, and I want to say very little of this is original with me. It's due to other people like Bucci originally figured this out, Hodgson. There's a beautiful paper of Brière, Hansel, Michaud, and Villemer that explains the theory in detail. Christian Fournier and co-authors, Hamoun Mousavi, who implemented this, my co-author Luc Schaefer in his master's thesis, and Asim Baron-Wall, who's implemented the Ostrowski stuff. So I'm not going to go into that today. Okay, so what Walnut needs, if you want to use it to solve a problem, you need to choose a regular enumeration system. And the default, if you don't specify, is base 2. So you'll notice in that example with 2A Morse, we did not specify an enumeration system, and then the default was base 2. You need a DFAO that computes the sequence S, and some of them are supplied, like the 2A Morse sequence was called T, and others you can just define yourself. And then you need a first order formula involving variables, quantifiers, logical operations, addition and subtraction of natural numbers, and indexing into your sequence. And once you have those three things, then Walnut can say true or false. So I want to point out that you can't multiply or divide with variables. But you can multiply or do integer division with a natural number constant. In other words, you can write 2 times x, but you can't write down y times x. So 2 times x is just understood by Walnut to mean x plus x. Because the domain of variables is assumed to be the non-negative integers, subtraction must not result in a negative number. So if you have 2 variables, x and y, you're allowed to write x minus y, but the assumption is that x is greater than or equal to y. And if you allow negative numbers to occur, even as sub-expressions, then the results are unpredictable and may be wrong. So you have to be a little bit careful about that. And you can't, the values of a sequence are basically just symbols, although they are integers, and you can't do arithmetic. So you can't say something like ti, the ith symbol of t, plus tj, the jth symbol of t. Even though 2A Morse is defined over 0, 1, you can't do that, at least currently. But you can compare them with less than or equal and so forth. And there's a natural ordering on the sequence values, which is the ordering on Z, the integers. So 0 is less than 1 and so forth. Okay, now what does Walnut produce? If the logical formula has no free variables, and by free, I mean not bound to a quantifier, then Walnut produces either the answer true or false. And the newer version actually just prints out true or false. If the logical formula has 1 or more free variables, then Walnut produces a DFA that recognizes the representations of the values of the free variables that make the formula true. So for example, suppose I type in the formula n greater than or equal to 6. And I ask Walnut to evaluate the formula n greater than or equal to 6. Then what I get back is this automaton. And what does this automaton recognize? The set of all base 2 representations of numbers that are greater than or equal to 6, right? So let's see, 6. 6 is 1, 1, 0, so 1, 1, 0. That's accepted because of the double circle. And how about 5? 5 is 1, 0, 1. That's not accepted because it's a single circle. So if there are one or more free variables, what you get back is an automaton like this. And I'll explain what I mean by you get an automaton in a second. Any questions? Okay. So here's the quick guide to Walnut syntax. As I said, capital A means for all, capital E means there exists. Ampersand means and, straight bar means or, a twiddle means not. This sign means implication. This sign means if and only if. The arithmetic operations are plus, minus, times, and integer division. And as I mentioned, you can only multiply by constants or divide by constants. Def defines an automaton or a macro that can be used later with multiple arguments. So I can define the notion of this factor of this sequence is a palindrome. And then I can use that as a subroutine later on. Eval evaluates a statement and returns true or false. Reg defines a regular expression. So for example, in base 2, if I want to say this number is a power of 2, the way I can do that is I can say, let's define a regular expression for the symbols that start with 1 and then have any number of zeros. And then if it matches that, the number is a power of 2. So I can make a formula that says n is a power of 2. This funny syntax says, do a query, that's the question mark, in the most significant digit format in base 3. So that means all the numbers are represented most significant digit first and are assumed to be in base 3. And you can also say MSD fib, that means Fibonacci representation, or LSD2, that means least significant digit first in base 2, and so forth. So this tells how to evaluate a formula. And the default is MSD2. At 0 represents a sequence value 0. So if you want to say the ith symbol of the 2A more sequence is 0, you have to compare it to at 0 rather than 0, because sequence values are not the natural numbers. They're just sort of arbitrary labels. And you can't do arithmetic with them, and hence they're distinguished in this way. When you call a multi-parameter macro, the order of parameters is alphabetical in terms of the original definition. Maybe this is not the most clever way to do things, but if you define a macro with variables A, B, and C, then when you call it, A is the first argument, B is the second, and C is the third. Okay, now let's just review how you can express various kinds of bounded quantification, which is what you typically want to do. So if you want to say for all n greater than or equal to t, p of n holds, in Walnut you say for all n greater than or equal to t implies p of n. And you put the $sign when p is something previously defined. To say that there exists an n greater than or equal to t such that p of n holds, you say there exists n such that n is greater than or equal to t and p of n. And to say p of n holds for infinitely many n, you say for all m, there exists an n which is bigger than that m such that p of n holds. Okay, so just keep in mind that if you want to express various kinds of bounded quantifications, then you need to use these formulations. Maybe eventually that'll change so that you can write it more like this. But for the moment, this is what you need to do. Okay, let's look at a second example. Let's look at antipowers. So Fici, Restivo, Silva, and Zamboni published a beautiful paper in 2018 where they invented this notion called antipowers. So remember that a power is R consecutive identical blocks. For them, an R antipower is R consecutive distinct blocks, all of the same size. So let's look at the word entanglement. This is a 3 antipower because when you break it up into 3 equal sized blocks, all the blocks are distinct. But it's not a 4 antipower because if you break it up into 4 blocks, the first and last block are the same. So they studied in particular this Cantor word. And what's the Cantor word? The Cantor word is the fixed point of this morphism. 1 goes to 1, 0, 1, 0 goes to 0, 0, 0. And the one that starts with 1, because the one that starts with 0 is not so interesting. So they proved, Uffizi, Postic, and Silva proved that the Cantor word avoids 11 antipowers. So there are no 11 antipowers, no 11 consecutive distinct blocks. So we can prove this a little bit with Walnut too. The Cantor word contains no 10 antipowers. That's the optimal because it does contain a 9 antipower. So this was proved by my master's thesis, a master's student, Samin Riasat, in his thesis. So how should we do this? Well, for the 9 antipower, you can just find one, and Walnut will find one for you if you want, but you could just write a short program yourself and find a 9 antipower. You check that all these 9 blocks are distinct. To show that it has no 10 antipowers, what you need to do is you need to show that every block of size 10n inside of it can be split into 10 consecutive blocks of size n, with at least 2 of these being identical. So at first glance, it would look like you need to compare 45 different pairs of blocks, right? There are no 10 antipowers provided for all I and n. I is the starting position, n is the n. There exist some blocks k and l between 0 and 9, such that if I compare, this is a macro to compare 2 consecutive blocks starting at different positions. If I compare the block of length n starting at position I plus kn, then it's the same as the block starting at position I plus ln of size n. So if there always exists such k and l, then there would be no 10 antipowers. But the problem is that although this is a first order statement, it uses an unallowed operation, which is multiplication by an integer. But we can just unroll this, right? Because this is just k and l between 0 and 10. We can unroll this into 45 different statements. And we can run Walnut on that. But luckily, we don't have to. We can do some experimentation to see which blocks it suffices to look at. And so when we do that, we get a conjecture like this. This says, if you look at the block starting at position I and compare it to I plus n, or I and I plus 5n, and so forth, that these suffice. It suffices to, one of these is going to be the same. So I've cut it down to only 14 blocks. And now I have a Walnut statement that I can actually fit on a page. And when we run this through Walnut, right away, it comes back to with true. So there are indeed always 2 consecutive, two blocks of the same size. And so there are no 10 antipowers. Any questions?
So there's if you did it for 45, would it be still fast?
Yeah, still fast. I just didn't want to have to write a whole thing all over the page.
So it could be there could be a bounded quantification could be somehow supported in the syntax. No.
Lots of things could be done.
So okay.
Yeah.
Okay, but in principle, right, bounded quantification in general is allowed.
Well, if it's like this, yeah, if it's some fixed number of things, yeah. Yeah. Okay, so let's look at another example. Let's recall that a word is bordered if it begins and ends with a non-empty word different from W. And like the word meantime, it's bordered with border me. Curry and Sari, in a paper in 2009, they studied the unbordered factors of the 2A more sequence. And they proved if n is not congruent to 1 mod 6, then t has an unbordered factor of length n. But t also has an unbordered factor of length 31. So their criterion is indeed sufficient, but not necessary, because here's 31, which is 1 mod 6, and t has an unbordered factor of length n. So this leads to the question is, what exactly are the lengths of the unbordered factors in 2A Morse? And if you look at their proof, it's a long kind of case-based proof. It'd be nice if we could just write this down as a first order statement and let Walnut work with it. So we can do that. So here's a little picture. Here's the 2A Morse sequence starting at position I and going to position I plus n minus 1. That's a factor of length n, beginning at position I. And what does it mean for this factor to be unbordered? It means that there's no block in green starting at position I and going to some position I plus j minus 1, in other words, a block of length j, that exactly equals a block of length j at the end. And so we can translate this into Walnut. TM has board. That's saying, does it have a border? Is the length n factor of t beginning at position I bordered? This should say n and I are unbound variables for this one. And then I've just translated this formula. I say there's a j. J is at least 1. J is not n, because that would be the whole word, such that for all t, the symbol here at position I plus t is the same as the symbol here at position I plus n plus t minus j. That's this position here. And there it is. And then to get the lengths, you just say, does there exist a position I, a starting position, so that there is an unbordered factor, that's why there's a not here, starting at the position I of length n. And so unboard length has n as an unbound variable. So what is it going to produce? It's going to produce an automaton that recognizes exactly the base 2 representations of those n for which there's an unbordered factor. And if we look at this automaton, we see that there's one non-accepting state. And so we see that t has an unbordered factor of length n if and only if n in base 2 is not of the form 1, 0, 1 star 0, all starred, 1, 0 star 1. That's the only path that leads to a non-accepting state. So we've proved this theorem. So this is a complete characterization, which we got with no case analysis at all, and just let Walnut do all the work. So I will answer Sada's talk in just a second. Sada's question in just a second. So now when I say it gives you this automaton, what do I mean? Well, so let's exit and see what we get. So let me go back one slide, and for some reason it's not letting me select. I don't know why. Why isn't it letting me select this? Maybe it has to be in full page mode to do that. I don't know. No, it's not letting me select this. Okay.
I think
anyway,
if you go to, sorry, if you go to like next to 209, if you go to, yeah, click that.
okay.
I think it will work.
Okay. Let's see.
Try.
Good. Thank you.
No
Okay.
problem.
So I just take this and I cut and paste it into Walnut. There's the first one. It took 405 milliseconds. And now the second one, cut and paste it. And now what it does, it has produced a bunch of things. So let me show you what it's produced. So here, it's produced a text file. The text file here, may be hard to see, is a description of the automaton. It says it's expecting most significant digit base 2 as the input. There's a state 0 with output 1. There's a state 1 with output 1. There's a state 2 with output 1. That means accepting. There's a state 4 with output 0. That means not accepting. From state 0 on input 0, you go to 0, 1, you go to 1, and so forth. So there's an encoding of the automaton. It also produces this .gv file, which for those who know is a graph visualization format that describes the automaton with circles and so forth. And then finally, if you can convert that GV format to an automaton, which is exactly the one in the picture that I showed you. So that's what, when I say it produces an automaton, that's what you get. 3 different formats that you can play with. Any questions about that? Okay, let me go to Sada's talk. Sada was talking about the Cantor example and asked, was the process in reducing 45 cases to 14 cases, was it random? So no, it wasn't random. What I did was I just took the word and I said, okay, let's look at all the 45 cases, and we know, since we're conjecturing there's no 10 ND powers, that one of these cases must always work. And let's start throwing out cases and see if that continues to be true on a prefix of length 100,000. And just keep doing it until we got a place where, oh, it's no longer true, and then restore the one that you got rid of, and I ended up with 14. So I'm not even claiming it's minimal. But this is the kind of game you can play. If you have a conjecture, you can, modify the conjecture and try Walnut to try it out and see if it's right. So that's it. So it's a tool. It's a tool for, you might have a conjecture about something being true, and you can just immediately try it out and see whether it's proved or disproved. And these are rigorous proofs and disproofs. So, you don't have to worry that something has been missed. All right. So there, we got this, we proved this formula. Okay, so now we can say, well, which n did the Curry characterization miss? Well, you just define that it's unbordered length of n, and n is not congruent to 1 mod 6. So 6 times the integer division of n over 6 plus 1 is those n that are 1 mod 6. And now we get a DFA, which shows exactly the ones that they missed. For example, 1, 1, 1, 1, 1, that's 31 in base 2. And you can see that if I go 1, 1, 1, 1, 1, and I can go back and forth with ones, so they missed infinitely many cases. For example, they missed 2 to the 2k plus 1 minus 1. So, you can do this kind of thing, saying, well, here's my conjecture. Oh, it's not quite right. What did I miss? You can do this. All right, let's look at an example, next example. And this one is the combining Walnut with automated heuristic search. I really like this, and I hope it will be useful to some people. You want to construct an infinite word with some property. For example, an infinite binary sequence with only 3 distinct squares. So this was studied by Frankel and Simpson. And they say, okay, let's, they constructed one in some rather difficult way, very ingenious, but still difficult. And now let's guess that there's some example of this that's k automatic for some k. So what we can do is we can just do breadth first search on the space of all binary sequences. And at every step, the strings that we are looking at are guaranteed to have at most 3 distinct squares, because we check that. And we also use like the Myhill-Nerode theorem to say that the sequence that we've produced so far will be recognizable by an automaton in base k with at most s states. And now we just do this for all k greater than or equal to 2 and ks less than or equal to some bound b, which we set. Maybe b is 50, something like this. So this is very easy to do. It's not built into Walnut, but you can easily write this code. And for each automaton, what you do is you then, the sequence that you get is recognizable by some automaton whose structure you can deduce with the Myhill-Nerode theorem. And then you run that automaton with the first 100 or 200 or 400 or 800 integers and see if the result still has at most 3 squares. If it seems to, then you have a candidate. And then you can run that candidate through Walnut because there's a first order formula for having at most 3 squares. So we did this and we got a 2 uniform morphism on 22 letters. In other words, a 22 state automaton. And the fixed point of this morphism followed by this coding gives you an infinite binary word with at most 3 squares. And Walnut can then complete the proof that this is it. And this is in some sense the simplest. Simplest meaning generated by a K automaton with the smallest state alphabet product. So the point is that this just requires a small amount of coding, then you get your example, you prove the example automatically, you're done. Let's go to the next example, Dean words. So recent preprint of Haryu discussed a paper of Dean in 1965 about square-free words over a 4-letter alphabet, namely XY, X inverse, Y inverse. So these are words that are considered then over a free group and that are not reducible. And reducible means you don't have an X next to an X inverse, which would cancel it, or vice versa. And the same thing for Y. So we can code these by saying, okay, 0 is X, 1 is Y, 2 is X inverse, 3 is Y inverse. And then what we want is we want a square-free word over this alphabet that has no 0, 2 or 2, 0 or 1, 3 or 3, 1 in it. So again, we can use breadth first search to look for a candidate automatic sequence. And when we do that, it quickly converges on this sequence, which only needs a 4-state automaton. And now we can prove that it is. We now make a new automaton from that. We call it de.text. We put it in the word automata library. Now we have a new automaton, new sequence that we can work with based on this automaton. And then we just check. Is there a square? Are there zeros and twos next to each other? Twos and zeros next to each other, and so forth. And all of these things return false. So there's no squares, there's no 0, 2, there's no 2, 0, there's no 1, 3, there's no 3, 1. Now, this is pretty simple. Some of this you could do without using Walnut, but the point is you don't need to do much work to verify it. And now I showed this to Haryu, and he says, oh, this looks interesting. The even index terms are 0, 2, 0, 2, 0, 2 forever. And the odd index terms, they look odd. And I said, oh yeah, that looks sort of like the regular paper folding sequence. So we can check this. Is it true that the symbol at position 4 times n is 0, and the symbol at position 4 times n plus 2 is 2? Is that true for all n? And is it true that the odd index terms, if they're 1, that's like the paper folding sequence, p, being 0, and if the odd index term is 3, that's like the paper folding sequence being 1. And in fact, we can then run these through Walnut, and both of them return true. So we know the structure of this sequence then. So this is a way Walnut can compare 2 different automatic sequences. This expression is comparing this automatic sequence DE that we just made with a built-in paper folding, regular paper folding sequence. So you can do that. Okay, let's look at example 7. Example 7 is about quasi-periodicity. So we say an infinite word is quasi-periodic if there's some finite prefix, call it Z, that covers X by shifts, allowing overlaps of these copies of Z. So can we cover all of X by writing Z above it, matching the symbols, and having no missing pieces, and these Zs can overlap each other? Such a Z is called a quasi-period. So if an example is ABA covers this string by shifts, so I can put an ABA there, and then an ABA there, and then an ABA there, which will overlap the second ABA. So we can write a first order logical formula for this. It says that for all positions I, there exists a J such that J is less than or equal to I, and I is less than N plus J, such that for all L, the symbol at position L is a symbol at position J plus L. So in other words, what this is saying is that the prefix of length N is a quasi-period. And there was a paper of Christou, Crochemore, and Iliopoulos in which they proved, more or less, that a length N prefix of the Fibonacci word is a quasi-period of the Fibonacci word F, if and only if N is not of the form 1 less than a Fibonacci number. So we can prove this. Let's see how we would do this in Walnut. Well, first we define something for two factors of the Fibonacci word to be the same. The one beginning at position I and the one beginning at position J, both of length N. So fib factor eq, using a Fibonacci representation of numbers, asserts that the factor of length N beginning at position I is the same as the factor of length N beginning at position J. Then isFib asserts that a number is a Fibonacci number because it says its Fibonacci representation looks like 1 followed by zeros, and I allow leading zeros. So that if you know Fibonacci representation, you know that that means the number is a Fibonacci number. And then fib quasi asserts that F is quasi-periodic with period N. I just wrote down in Walnut the translation of the previous page. For all I, there exists a J such that if I cover the ith position with a length N factor beginning at position J, then it's the same as the prefix starting at position 0. And then I say, all right, now I'm going to make the assertion that for all N, the length N prefix of the Fibonacci number is a quasi-period if and only if N plus 1 is not a Fibonacci number. There's the not. And it returns true. And similarly, you can prove that the 2A Morse word is not quasi-periodic. There's no prefix that you can use to cover the whole 2A Morse sequence. So here we recover well-known results. But the nice thing about Walnut is then this immediately suggests generalizations that you can test. And you don't need much work to test them. You say, okay, well, 2A Morse, not quasi-periodic, but could it be 2 quasi-periodic? That is, could you tile the 2A Morse word with 2 distinct words? Now, of course, you can. You can tile it with 0 and 1. But you might say, well, what are all the pairs of words that you can tile it with? So obviously, you can tile it with 0 and 1, but you can also tile it with 0, 1, and 1, 0. Are there any? And 0, 1, 1, 0, and 1, 0, 0, 1. So all the iterates of 2A Morse on the 2A Morse morphism, you could tile it with those two, those pairs. But are there any others? And Walnut can tell you that. So here's the theorem, which as far as I know is new, but it's not a big theorem. But the point is that it allows you to state these generalizations and then just check them immediately with very little work. So T can be covered by these 2 pairs, mu of n of 0 and mu n of 1 for any n, and mu of n of 0, 1, 0 and mu to the n of 0, 1, 1, 0. Those are the only ones. And you can prove that. Any questions? Okay, let's go on. Example 8. Now I said there are 10 examples altogether, and I'm going to spend the second half talking about enumeration things. So let x sub a, absolute value x sub a, mean the number of occurrences of the letter a in x. And we say a word is balanced if for all equal length factors y and z of x, and all letters a, the number of occurrences of a and y minus the number of occurrences of a and z differs by no more than 1. So in other words, a word is balanced if all letters occur with essentially the same frequency. So for example, banana is balanced, right? So ANA has 2 A's, NAN has 1 A, but that only differs by 1. But apple is unbalanced because LE has no P's, but PP has 2 P's. So the P's there are unbalanced. So a priori, there's no obvious way to state this definition in first order logic, because we need to count the number of A's. And I don't know any way to do that with the kinds of operations that we have in first order logic. It seems like you have to count the cardinality of some finite subset with a given property, and I don't see how to do that. But luckily, people have studied balanced words very extensively, and you know that there's an alternate characterization of balance for binary words. A finite or infinite word x is balanced if and only if it contains no pairs of factors of the form 0v0 and 1v1 simultaneously. So that is a first order assertion. So we can create a formula asserting that this factor is an unbalanced factor by asserting that somewhere in there is 0v0 and 1v1, that there's indices left 1, right 1, left 2, right 2, such that x L1 R1 is 0v0 and x L2 R2 is 1v1. So putting this all together, we need I is less than or equal to L1, which is less than R1, which is less than I plus N. And similarly for L2 and R2, that these words are the same length. So R1 minus L1 is R2 minus L2. That L1 and R1 evaluate to 0 and L2 and R2 evaluate to 1. And that the internal factor, that is the V part, is the same. L1 plus 1 to R1 minus 1 is the same as L2 plus 1 to R2 minus 1. And for the Fibonacci word, here it is. It says unbal fib. There exists this L1, L2, R1, and R2. All these conditions hold. And the internal factor is the same. And this asserts that this factor, beginning at position I and of length n, is unbalanced. And then we can just make the assertion that for all I and for all n, every factor is balanced. And of course, this is well known that this is a property of the Fibonacci word, and indeed any Sturmian word, but Walnut tells you, yeah, this is true. So every factor is balanced. So this only worked because we had a first order characterization of this property. For 2A Morse, we can do the same thing, and then we can see that in fact, most factors of T are unbalanced. It only has balanced factors of length T, less than or equal to 8, and nothing else. And of course, you could do that just by searching through the factors, because once you get to all factors of length 9 are unbalanced, then all larger factors will also be unbalanced. Okay, let's look at example 9. Linear recurrence is a property of sequences. And what I mean by linear recurrence is that there's some function g, which is big O of n, such that every occurrence of a factor or block of length n in x is followed by another occurrence of the same factor and not too far away, at distance at most g of n. So the distance here is the difference in the indices of the starting points of this occurrence of the factor. So that says that 2 consecutive occurrences of a length n factor occur not too far apart, at most big O of n apart. So in other words, there exists a constant C such that for all I and n, there exists a J such that J is between 1 and C times n, such that the factor at position I and the factor at position I plus J of length n is identical. Now, as stated, this is not first order expressible in our logical theory because of this multiplication C times n. But if we have a good guess as to what G might be, we can easily verify this guess. So if we knew C was 10, we could just type this in with C replaced by 10, and then it is a first order statement in our theory because we're only multiplying by a constant. And furthermore, we can verify that it's best possible. I won't go into the exact details, but this can be done. For the 2a more sequence, it turns out that G of n is 9n minus 18 for n greater than or equal to 3. And this is optimal. Okay, so let me stop just for a second because Matthew Rosenfeld had a question. He said, in the previous example with the balanced words, it says it seems more natural to have two positions, L1 and L2, and a length L instead of R1 and R2. Do you introduce them because the computation is more efficient? No, it was just, I go back and forth between trying to decide whether it's better to say starting position and length or starting position and ending position. And in this talk, I'm trying to give a wide variety of different ways to do things. We'll talk about efficiency in a little bit. He asked, do you introduce them because the computation is more efficient? I'll address this question in a little bit, okay? All right, so anyway, here's the proof with Walnut that this 9n minus 18 is optimal. It says, for all I and n, the next occurrence of I plus n minus 1 is at distance less than or equal to 9n minus 18. And you'll notice instead of writing 9n minus 18, I wrote j plus 18 less than or equal to 9n. That's, you know, the typical way you try to avoid subtraction and the problems that might ensue with subtraction. And here it says there are arbitrarily large factors where the next occurrence is at distance at least 9n minus 18. And both of these return true. So we're done. Okay, last example before I get into enumeration, and that's number theory. So additive number theory. So what's a sum set? If I have two sets of natural numbers, s and t, a sum set, s plus t, is a set of all numbers of the form little s plus little t, where the little s comes from big S and the little t comes from big T. So all pairwise sums. And number theorists study these like crazy, like, for example, Goldbach's conjecture. Every even number is the sum of two primes. Okay, so let phi be the golden ratio, 1 plus root 5 over 2. And the lower Wythoff sequence is this sequence here. And the upper Wythoff sequence is this. I guess probably it should be pronounced Withoff, but I'll say Wythoff. And these are two sequences of natural numbers. And recently, some mathematicians were interested in the additive properties of these things. So it was Cosamong et al. And they looked at these sum sets. So one of the theorems that they proved is L plus U plus U. So now that instead of pairwise sums, this is three-way sums, is the set of all natural numbers except these exceptions. And, you know, their proofs are ingenious, but long and case-based and complicated. And, you know, if you're like me, you always worry maybe some case was missed or you know, as you read it, you think, oh, well, maybe I missed something. But you can do this with Walnut. And how do you do that? Well, there's a very nice theorem due to Silber, which says n is in the lower Wythoff sequence if and only if the Fibonacci representation of n minus 1 ends in 0, and n is in the upper one if n minus 1 in the Fibonacci representation ends in 1. So that means that you can write this down with an automaton. being in L or being in U. So here, if it ends in a 0, that's this regular expression. If it ends in a 1, that's this regular expression. And then the lower Wythoff sequence is that n-1 ends in a 0, and the upper one is that n-1 ends in a 1. And now we have the Walnut code for these sequences. And now we can say, do there exist A, B, and C such that n is equal to A plus B plus C, and A is in the lower Wythoff sequence, and B is in the upper, and C is in the upper? And then I put a not there. This gives me the Fibonacci representation of all numbers not in the subset L plus U plus U. So if you didn't know the theorem, this would then give you the theorem, because the resulting automaton would characterize all the n. But if we already know the theorem, we can just look at the result and verify that indeed the only things that are not in L plus U are these guys accepted by this automaton, which is 0, 1, 2, 3, which is 1, 0, 0 in Fibonacci, 4, which is 1, 0, 1, 5 is 1, 0, 0, 0, it's not accepted, 6 is 1, 0, 0, 1, and 9, which is 1, 0, 0, 0, 1. So indeed, we recover their theorem with little work. Okay, so I've finished a bunch of examples. This might be a logical time to stop and take any questions before I go on to a different topic, which is how to do enumeration with Walnut.
I have a question about the quasi-periodicity of tumors. Is it true that no suffix of tumors is quasi-periodic? No.
One could do that. One could do that.
Because I was wondering, why do we take a prefix? But of course, the answer is that you have to cover the prefix.
So we would have to modify the formulas very slightly to allow a tiling with any factor, and then ask, does there exist a suffix that is tiling?
So it is not known, like.
Oh, I'm sure it's known. I'm sure it's known, and I'm sure the answer is no, with a single word. But I mean, if you're asking me to do this example, we could probably try to cook it up at the end.
Okay.
Yeah.
I can probably say that if you have a overlap-free word, then all quasi-periods are periods.
Okay,
so
great.
Probably this is a simple answer.
Okay.
That you have no quasi-periodic suffixes.
Okay, that's great, and I'm happy to know that. But the point being more not what the theorems are, but what you could do and how you could do it. That's the theme today, if you don't mind, right? I would to me the goal is to show how to make these predicates and what you can do with them. And sometimes you'll end up doing something completely trivial, because if you think about it for 10 seconds, you would see that what you want is true, right? Anyway, okay, so I guess I should say that Walnut shouldn't be a substitute for thinking about things, but sometimes it's useful to use it to think about things that you just want an answer right away, or they're too complicated for you to prove by hand. That's the value. Okay, we can use Walnut to find a representation for various integer valued functions. And the simplest is the linear representation for a function. So a linear representation for a function is a way of writing f of n as a row vector u dotted with some matrix product gamma of x dotted with a column vector v. And here gamma is a matrix valued morphism that is applied to the word x, and x is the representation of n. So if you have such a representation, you can compute f of n very efficiently, because all you need to do is represent x in the representation system that you want and evaluate this product. So we can do this for subword complexity of the 2A-more sequence, for example, which was previously done by Berlek and DeLuca and Varicchio and Augustinovich independently back in the late 80s, if I remember right. So here, f of n is the number of distinct length n factors of t. So how do we do this? What we do is, to compute this f, we're going to count the number of length n novel factors. And what do I mean by novel factors? I mean those beginning at some position I, but not occurring at any earlier position. So that means this is, as you read from left to right in the sequence, this is the first occurrence of this particular factor. So if we count how many first occurrences there are, novel factors, that's the total number of distinct factors. So here's Tm factor equal, you've seen this many times. This is the length n factor beginning at position I and position j are the same. This says for all j, if j is less than I, then the factor beginning at position I and j are not the same. In other words, t from I to I plus n minus 1 is a novel factor. And you'll notice this is slightly different syntax here. There's an n here that never appeared before. What this says is make a linear representation for this function that counts with respect to the variable n the logical formula that follows. In other words, how many novel factors there are of length n. So how many, the only free variables here are I and n, and here we fix n, so it's the number of I, so that's the number of novel factors. And the output here is a maple file with the definitions of u, gamma of 0, gamma of 1, and v, which then allows us to compute this efficiently. So now, for technical reasons I won't go into here, the output of Walnut, that the u that you get, actually is not quite the u that you need. What you need is you need to replace u by u gamma 0 until the value stabilizes. And this gives you this linear representation here. It gives you this u prime, gamma of 0, gamma of 1, and v. And now f of n, which is the number of distinct length n factors of t, is this thing. And this gives us an explicit formula for f of n that we can evaluate in log n cubed time. So much more efficient than listing all the factors and counting them. And furthermore, because we have this matrix representation now, we can get an exact formula for f of 2 to the n, because what is 2 to the n in base 2? It's 1 followed by n zeros. So that's like gamma 1 followed by the nth power of this matrix. And therefore, we can get an exact formula for f of 2 to the n in terms of the eigenvalues of gamma of 0. So here, f of 2 to the n is u prime gamma of 1, gamma of 0 to the nv. Every entry of the matrix gamma of 0 to the n satisfies a linear recurrence that corresponds to the minimal polynomial of gamma of 0. And then we can just use maple to say, what's the minimal polynomial of that 8 by 8 matrix? And we get that it's this thing. And now f of 2 to the n is going to be a linear combination of the entries of gamma 0 to the n, right? This is a linear combination of these entries. And so it's going to satisfy this linear recurrence too. And then by the fundamental theorem of linear recurrences, it says that f of 2 to the n then is going to be some constant times 1 to the n plus some constant times 2 to the n. A times 2 to the n plus b times 1 to the n. So it must look like this. And now we can simply use linear algebra to solve for a and b by substituting two values of n, like n is 0 and n is 1. Well, I'm sorry, this is only true for n greater than or equal to 2. So for n equal 2 and n equal 3. And the reason why it's only true for n greater than or equal to 2 is because we have this factor of x squared in the minimal polynomial. And then we substitute two values of n, and we find a is 3, b is minus 2. And so we get f of n, sorry, that should be f of 2 to the n, typo there. F of 2 to the n is 3 times 2 to the n minus 2. So there we get an exact formula for the number of factors of 2A Morse of length 2 to the n. All right, so that's one way to do it. I'm going to give two other ways of finding the subword complexity of 2A Morse. So there's a theorem of Ksenia that says that the first difference of a subword complexity of any sequence of linear complexity, in particular an automatic sequence, is bounded above by a constant. So now what is the first difference of the subword complexity? It's the number of length n factors that are right special. That is, both x0 and x1 occur. And I'm talking about binary sequences now. So we can count those. We can say right spec, that's the assertion that the factor beginning at position I of length n is right special. It says that the factor at position I and the factor at position j are the same, but if I look at the very next symbol, I plus n and j plus n, they're different. That means it's a right special factor. And then I could say, okay, count the right special factors that are novel. And this is that never occurred before. And this gives us a representation of rank 6 for this first difference. Now we can minimize this using an algorithm of Schützenberger. And this is discussed in the book of Berstel and Routenauer. I have Maple code that does this, which I can share with anyone. And it gives us a minimal linear representation. And now we can turn this minimal linear representation. Remember that the first difference of the subword complexity was bounded. So there's only finitely many values it takes. They're all integers. They're all non-negative integers. So we can turn this into DFAO, where the states are 4-element vectors. The initial state is this vector. You go from state to state by multiplying by the appropriate gamma value matrix. And the output is the state dotted with this V. And when we do that, we get this DFAO, and this computes the first difference of the subword complexity for 2A Morse. So for example, if we want to know how many right special factors are there of length 5, we go 1, 0, 1, and it says 4 of them. So the number after the state name is the output. And here are the 4 right special factors of length 5. Okay. So, okay, now the third way we can do right special subword complexity is via synchronized sequences. And this is the most fun of all, and the one that gives you the most information. So as we've seen, subword complexity is the number of length n novel factors. So I observed, and Luke Schaefer later proved, that for automatic sequences, the starting positions of the length n novel factors lie in a finite number of clumps. And by clumps, I mean starting positions in the word. The starting positions are consecutive in the word. So we can compute the subword complexity by adding up the lengths of the clumps, right? So if the length n novel factors are clumped together in a finite number of clumps that you can figure out what the bound is, then you just say everything inside the clumps, you add up how many there are. And that you can do because the length of a clump is just the ending position minus the starting position plus 1. And everything outside the clumps are not novel factors. So we can do that. We guess the left and right endpoints of the clumps. We don't know them. And then we verify that inside the clumps, all the length n factors are novel. Outside, they're all not novel. And for 2A Morse, it turns out that one can prove, or one can compute with Walnut, that there are at most 5 clumps for each n. Basically, the number of clumps is no more than 1 plus the first difference of the subword complexity, which we already just saw was at most 4. So there are at most 5 clumps. And now we write this sort of horrendous Walnut code where we guess the left and right endpoints of the clumps, namely A1, B1, A2, B2, A3, B3, A4, B4, A5, B5. You'll notice there's no A1 because the very first factor has a left endpoint of 0, so we don't need to guess it. And then we simply say that they're all novel inside the clumps, and they're all not novel outside the clumps. And then we say the total number of factors is the sum of the sizes of the clumps. There it is. This is kind of a horrible thing, but we type it in. And despite the fact that there are 9 quantified variables, it gives us a 14-state automaton that recognizes in parallel the base 2 representations of n and f of n. In other words, the subword complexity function is synchronized, which was the result of our paper. And you can use those results then to find this synchronized automaton. And now once we have the synchronized automaton, we can do everything with it, because we could verify this formula due to, I think, Berlek, that says exactly what the subword complexity function is. If n is 2 to the r plus I, and I is between 1 and 2 to the r minus 1, then it's this expression, and otherwise it's this expression. And there we can just check it. Here is this assertion translated into a first order statement. You can see there's the 2 times I less than or equal to x s plus 4 is 3 times x. Here x is a power of 2, 3 times the power of 2 plus 4 times I minus 4, that's and so forth. And we check it and we run this through Walnut and it says true. So we verified this formula. So synchronized representations for functions are the most useful because we can use them to prove guessed exact formulas like the one above. So that's 3 different ways you can use Walnut to do enumeration of various things. Any questions about the enumeration ideas? Okay, I hope you're all still there. Now, unfortunately, it's not always possible to find a synchronized representation for a function given by a linear representation. There are not always these things, but often there are. Okay, I'll give one more example. You might say, well, what good is Walnut? You know, you're only proving facts about specific sequences. And the answer is that you can sometimes use it to prove facts about many sequences. In fact, uncountably many sequences. So the paper folding sequences are an uncountable set of infinite sequences, each one determined by a specific infinite sequence of unfolding instructions. And the unfolding instructions are U0, U1, and so forth. We start with the empty word, and we take the ith paper folding word, we stick in the unfolding instruction, and then we negate and reverse the previous paper folding sequence. And the limit is the paper folding sequence with this unfolding instructions. Now, it turns out that there's a single finite automaton that specifies all these sequences at once. It takes as input n in base 2 in parallel with the unfolding instructions and returns the ith bit of the appropriate sequence that should be of the appropriate sequence, not unfolding instructions. So we can prove assertions about some or all of them using this one automaton in Walnut. For example, a theorem of Alouche and Bousquet-Milou, which said that no paper folding sequence contains a repetition larger than a cube, that's also called a 3+ power. And here's a Walnut command that says, here it's quantifying, it's making the assertion that there exists some cube, there exists a set of folding instructions F, and here's the assertion that there is a power larger than a cube, and this returns false. So we've proven a theorem about uncountably many sequences at once. Okay, I'm winding down now, so I'm just going to talk briefly about some aspects of the practicality of using Walnut. Any quick questions? Can I get one person saying something out loud so I know everyone's still there?
I have a question.
Oh yeah, good.
So I'm wondering, now we have come to the saving time with the code. For example, when you were running code to verify something about the 2-more sequence, it's only like one sequence.
Right.
And then you do these paper folding, which are uncountably many. Did
Right.
you observe a time, like significant time difference?
No, because it's only a 5-state automaton, so it takes less than a second.
Okay.
Takes less than a second. Yeah.
Okay, cool. Thanks.
Yeah. So, but you raise a good question: is what makes it take a lot of time? And generally speaking, more alternating quantifiers, and more states. So I have worked with automata of up to like 100 states. And I have worked with as many as like 5 or 7 alternating quantifiers, and it can do it, but it gets slower and slower and slower. And actually, it's not so much the time, but the space that's prohibitive. So for example, here's a very, very simple logical formula that asserts that the length n factor beginning at position I of the Fibonacci word is the same as the length n factor beginning at position j. And there is a simple way to assert this. And this does not halt. At least I could not get it to halt, even if I allocate 120 gigs of storage. So the magical incantation to do that is this, at least on Linux. So if it doesn't run to completion, you don't get an answer. You don't learn whether it's true or, you don't, here you want it, it's not a true false statement. You want an automaton that can compare factors of the Fibonacci word, and it does not give you an answer. But you can often reformulate your query in some other way that you will get an answer. And then the answer is surprisingly fast sometimes. So here the problem is that you've indexed by 3 different variables, I, J, and T. And that's creating a rather large automaton, which it then has to determinize, and it just can't do it. So the idea is how to reformulate this assertion that the length n factor beginning at position I is the same as the length n factor beginning at position j using fewer variables. And here's how we can do it. We can say, is the symbol at position x the same as the symbol at position y? Now I only have 2 variables. For all x and y, such that x is bigger than I and smaller than I plus n, and what's the relationship between x and y is that x minus I should be y minus j, right? That's what it means. And so x plus j is y plus I. This is logically equivalent. Well, this is mathematically equivalent, sorry, to the previous statement. And this only takes 35 seconds of CPU time and uses only 7.2 gigs of storage and gives you back a 26-state automaton. So I guess the lesson is that like many things, you need to sometimes go at it from the side rather than head on to get what you want. Limitations of Walnut: only works with automatic sequences, not with arbitrary morphic sequences. No hope of doing that in general, because the characteristic sequence of the squares is a morphic sequence, and the first order theory of n plus and square is not decidable. Some queries might require ridiculously large amounts of time and space. For example, determinizing a 3,000 state NFA. Possible it could take 2 to the 3,000th time, in which case we're not going to see the answer in our lifetime. Can't be remedied in general because there's a double exponential lower bound just for Pressburger arithmetic, and this is a more powerful theory than Pressburger arithmetic. In practice, I would say 99% of my queries run to completion or can be rewritten like we just did with Fibonacci to do so. You can work with 2 or more sequences at once, but only if they're defined over the same enumeration system. So 2A Morse and Rudin Shapiro can be compared, but not 2A Morse and Fibonacci because we use two different enumeration systems to define them. Things that Walnut can't handle because they're not expressible. Arbitrary words, the arbitrary members of sigma star. No, we can only handle factors of automatic sequences and simple variations on them. For example, you could take a factor of an automatic sequence with an arbitrary symbol inserted somewhere in it that you can handle. Arbitrary length scattered subsequences of automatic sequences can't be handled because you have to specify a subset where you're getting it out of. But if it's a fixed length scattered subsequence, like a scattered subsequence of length 2 or 3 or 4, that we can handle. Abelian properties of factors in general can't be handled because, again, that requires some specifying some permutation, more or less, which you can't do in the first order statement. Except in special cases like 2A Morse and Fibonacci, you can do it. Comparing the number of ones in two different factors, again, can't be done except in special cases. Adding up the elements of a factor, treating a factor of an automatic sequence as a list of numbers and adding them up, can't do that except in special cases. Checking to see if terms of one sequence are arbitrary linear combinations of another, can't do that in general, except if coefficients and number of terms are bounded. So lots of stuff you can't do, but lots of stuff you can do. All right, common pitfalls if you're using Walnut, things to watch out for. Forgetting to specify the enumeration system if it's different from base 2. Forgetting about edge conditions, that is empty factors. You're trying to prove some statement is true for all factors. Well, maybe this statement, maybe some statement is not true for all factors. Maybe the statement is true for the empty factor. So, you might have to rule that out. So for example, all conjugates of F of length n beginning at position I appear in F. You might write this down as some factor that's shifted. And the problem is that if you restrict your shifts here to shifts between 0 and n-1 by saying the shift size is of size t and t is less than n, then it's going to fail for the empty string because there is no integer between 0 and less than 0. So in fact, you need to write t less than or equal to n or special case 0. So this one caused me endless problems in something I was doing because I didn't realize this subtle problem for the empty string. Another mistake is using parameters in the wrong order. Remember that when you call something like fib shift, the parameters, it's expecting, the way fib shift was defined is the free variables are I, j, n, and t, and it expects you to give them in that order. So it expects the first thing to represent I in this formula, the second to represent j, and so forth. Sub-expression with subtraction resulting in a negative number has often sometimes caused problems in the past. The self-defined DFAOs must go in the right place, called the word automata library, and the name must not start with A or E, because if it starts with capital A or capital E, it thinks it's for all or there exists. Okay, all done now. It's 10:29. I promised till 10:30, so I'm almost there. First order properties of automatic sequences are now trivially decidable. Some properties at first glance don't seem to be expressible, but can be reformulated. Conjectures about enumeration can be easily verified if they involve synchronized sequences. You can replace long case-based arguments with a simple computation. Rephrasing your property in first order logic helps you make your definition precise. And your mind is now free to work on harder properties of sequences, such as abelian and additive properties. So just mention a few things that I don't know how to do. Is there a first order formula for balance property for words over a larger alphabet than size 2? Or for generalizations of balance, so like 2 balance? Can one produce automatic reformulation of queries to make them more efficient, like that trib fac eq statement we had to reformulate it to get it to run. Maybe you could do this automatically somehow. You type in a query and it reformulates it to make it run faster. A multi-core version of Walnut for things that don't run in a reasonable length of time. That might be fun. And then to download Walnut, you can click on this link in the slides. Thanks to the people who wrote it, Hamoun Musabi on the left, Asim Baranwal on their right. Thank you for your wonderful software. Thank you.
Thanks, Jeff. Does anyone have any questions for Jeff?
Yeah, if I may. I have two questions, Jeff. The first one is about the complexity, computing complexity of automatic sequences. In the 90s, there was a result by Brigitte Mosset, and she was able to compute the complexity of, I guess, fixed point of morphic sequences when the morphism has constant lengths. And she wrote a program that was working only on Macintosh, which was not giving the formula, but the values of the complexity for the first small values of n. So the question is, what kind of automatic sequences are excluded from your computation of complexity?
All of them work.
And you get a formula.
Well, you get you get a linear represent. So you're guaranteed to get a linear representation. That's one way.
Okay.
And they are also synchronized by this result of Schaefer. So once you get a synchronized representation for it, which is from that, you can prove pretty much anything you want about it.
Okay.
So that will work in any enumeration system that obeys the properties.
Okay, thank you. And my second question, if you don't mind, was when you said you can work with or play with two different automatic sequences, can you, for example, determine all words or factors that are common to, say, two Morse and Rodin-Shapiro?
Yes.
Of course, if you fix the lengths, that's clear. But for
no. You can determine all of them because you just say, does there exist an I and a J such that the TM I plus T is equal to RS J plus T for all T between 0 and n minus 1. And then it will list all the n's that for which there are factors in common.
Okay, and you get an automaton at the end.
You get an automaton at the end. In fact, I did that. The longest factor in common is of length 8 or something like this. Yeah.
Okay. Merci
beaucoup. It does it right away. So, I mean, we could do it right now if you want. So, yeah.
Okay. Thank you.
Yeah. Let's see. Def common. There exist I and J such that for all T less than n implies to a Morse I plus T equals Rudin-Shapiro J plus T. Let's see, are there any free variables here? Just n, right?
Mm-hmm.
Hopefully this will work. Yeah, 6 states. So it gives us a 6-state automaton, which gives you the n that work for it.
Excellent. Thank you. Nice.
Anyone else have any questions?
So thanks, Jean-Paul, for giving me an example I could do in real time without embarrassing myself. Yeah, sure, Seda, yeah.
So my question is rather simple. It's about the coding. I was confused about when you write eval and def. So def is for defining an automaton, you said, and eval is evaluating a statement. But when what you write after def is also a statement.
Yeah, so they're not that much different. Def, you use def when you want to you want to have the result as a subroutine you could later use. Like now I've defined common and I can say $common of n. and use it in some other thing. If you say eval, you can't use it later. That's really the only big difference.
And in the first example you did at the beginning about has overlap, I remember you wrote it as eval, but you wrote eval and has overlap. But did we define has overlap before that line, or?
That was the definition. Yeah. So if we
Oh,
go
so
back,
you don't have to define it.
here it
Okay.
is. Here's eval has OLAP, and the has OLAP is so when you give the name is assigned to the automaton for the formula that follows.
Okay.
Yeah.
Okay, thanks.
Sure. So maybe I should say that if anybody ever uses it in their research in any way that you think might be slightly novel, I would love to hear about it. So I try to maintain a page where I discuss what other people have used it for. And I think one could easily teach like an undergraduate course on combinatorics on words, where the goal was, come up with some new interesting properties of words and find words that exhibit these properties. It might be fun.
So are there any other questions for Jeff?
Is there any natural interpretation of what happens when you use negative numbers?
It's just that if you say, if you're asserting the existence of something, then if you kind of parenthesize the expression wrong, the thing might actually exist, but you won't find it. Like, for example, suppose you said something like I plus j minus k. Then if j minus k gives you a negative number, then there won't be any I plus j minus k to be discussing. So it kind of won't exist. Where if you said I plus j in parenthesis minus k, it would exist, right? There would be some triples. Let's say I plus j, I plus parenthesis j minus k equals 0. And now you ask for all the ijk that fulfill this. This will be different from the set of triples I plus j in parenthesis minus k equals 0. So you might get the wrong answer if you're expecting it to behave the same in both.
Okay.
That's the, I should get
A good example.
I should make a note to provide that as an example in general. Yeah. So I guess we could do it now. So def test 1. I plus j minus k equals 0. I'm always reluctant to do this because I usually make some stupid mistake. Def test 2, I plus j minus k equals 0. You can see the automata have different numbers of states. So they're not generating the same automaton.
Nice. Thank you.
Yeah.
Does anyone have anything else?
Thanks for everybody for sticking for such a long session, and I hope you get something out of it.
Well, thanks a lot, Jeff, for that tutorial. So our next talk will be in 2 weeks. We have Etienne Moutot